Hello and welcome to the Screencast introducing rational functions. Rational functions are ratios of polynomial functions. These arise naturally in several important settings in calculus, including the central topic of average rate of change, as well as in constrained optimization problems. Consider a setting we've encountered many times. We have a function s of t equals negative 16t squared plus 48t, and we want to consider the average rate of change of s on the interval from 2 to 2 plus h. After applying the average rate of change formula and simplifying, we find that the average rate of change from 2 to 2 plus h of the function s equals negative 16h plus 16h squared, all divided by h. Note that this expression involves the ratio of two polynomial functions, the quadratic function negative 16h plus 16h squared in the numerator and the elementary linear function h in the denominator. This provides just one motivating reason for why rational functions are important and why we might want to study them near points where they are undefined, here where h would equal 0. Like we've done for any family of functions that we've studied so far, for rational functions, we are interested in such questions as what patterns hold across all rational functions, how can we find where vertical and horizontal asymptotes lie for a given rational function, and what trends can we observe at special locations, both up close and from far away. Rational functions exhibit a wide range of interesting behaviors, including those seen in each of the following graphs. For example, we see that r of x on the left has a vertical and horizontal asymptote, while s of x in the middle only has a horizontal asymptote, and p of x on the right has neither a horizontal nor vertical asymptote, but does have a hole at the point 1, 0. We will learn more about how to understand the details of these features as we study rational functions in both this section and the next.